So we previously talked about a lot of definitions associated with chemistry, and one of those definitions was that an element is a compound composed of extremely small particles called atoms. All mercury atoms on the planet have the same atom combination. All oxygen atoms on the planet have the same atom combination, but mercury and oxygen do not have the same combination of atoms. Maybe that makes sense? I don't know. Compounds are composed of atoms of more than one element. So water is a compound. There's one oxygen and two hydrogens for all molecules of water, all compounds of water. Chemical reactions only rearrange compounds. They do not create or destroy atoms. They only rearrange how they're connected. So if I have these red atoms, element X, these green atoms, element Y, they can combine to form this compound. If you counted all these little dots, we have 16 red dots, maybe those are hydrogens, and 8 green dots, maybe those are oxygens. They can combine to form 8 molecules of water, 8 compounds of water. There's a reason I keep saying molecules. We'll get there in a moment. But we don't destroy any of the red dots or the green dots. We just rearrange them to make new stuff. That theory that says you cannot create or destroy atoms, that's called the law of conservation of mass. So today we're learning about elements and what elements are composed of. One of the big players who figured out what elements are composed of was Rutherford. He did this super famous experiment called the gold foil experiment and won a Nobel Prize for his experiment and what he discovered. The way the experiment worked was he had a gold foil, and he bombarded that gold foil with alpha particles. It's not super important that we know what alpha particles are right now, but it's a charged thing. It's a positively charged particle that when you spray out a laser beam of alpha particles and it comes in contact with this gold foil, he got different things to happen. So sometimes when that alpha particle is sprayed in, some of those alpha particles go through unchanged. Like this one, that arrow in and arrow out is exactly the same. It's straight. Some of them are unchanged. Some of them are deflected slightly, like this very top one up here. It's got a little crook in the middle of that arrow. Some of them are deflected more, like this guy. And some of them, like, basically bounce backwards. So Rutherford, super bright dude, what he figured out from this was apparently I have a lot of gold atoms all combined together, all packed in tightly in this gold foil. But the majority of the alpha particles that are sent toward that gold foil, the majority are undeflected. But some of them occasionally are totally deflected. Their path has changed a lot. Oddly enough, from this, he decided that an atom has a little nugget, a little core that is very dense right in the middle. And that was what was responsible for the backwards deflection here. So that little dense core he called the nucleus. And he also found out that nucleus is positively charged. So remember I said alpha particles are positively charged? One of the reasons they're deflected the way they are when alpha particles bump into the nucleus is because of their positive charge. There are other reasons too. We'll get into physics one day. So he said the nucleus is in the middle and it's very dense. The rest of the atom is a very not dense area. And so from that, we know that that's the electron cloud. The electron cloud is not very dense. So atoms are composed of protons, neutrons, and electrons. Protons and neutrons are the heavy particles in the middle, in the nucleus. Electrons are the big fluffy cloud all around the outside. Protons have positive charges, electrons have negative charges, and neutrons are neutral. The mass of a proton and the mass of a neutron are the same. That's the mass of a proton and the mass of a neutron. The mass of an electron is tiny. It's a little baby number. It's a tiny mass, takes up not much space in the electron cloud. Okay. So I started talking about neutrons, but actually Rutherford didn't exactly discover neutrons. This guy named Chadwick did that. So what he found was when he had a beryllium atom and he bumped an alpha particle, that's the symbol for an alpha particle, he bumped an alpha particle into a beryllium, he ended up with a carbon atom, a neutron, and he got energy out of it. Neutrons were not known prior to this little Chadwick experiment. So what he discovered was that you had a little bit of mass loss, and that little bit of mass loss, like I said, he attributed to a neutron. So this kind of equation is what's known as a nuclear equation, meaning reactions are happening in the nuclei of atoms. This number plus that number has to always equal the sum of numbers on the other side as well. So when he knew he got out a carbon, he knew he was missing one mass unit, and he found it. It was a neutrally charged species. He called it a neutron. So a neutron, like I just said a minute ago because I got ahead of myself, a neutron has the exact same mass as a proton. They are both considered heavy particles, and they are in the nucleus of the atom. Here's a table summarizing this, kind of. A neutron and proton have the exact same mass. They're considered heavy. This number is way bigger than that number. Electrons are very light particles. So protons, neutrons, electrons, those are all considered subatomic particles, meaning smaller than an atom. Atoms are composed of these particles. Electrons have a -1 charge. Protons have a +1 charge. Neutrons are neutral. Because protons and neutron masses are the same, we actually use a different unit to talk about their mass sometimes. So we can say a proton has the mass of 1 AMU, where AMU stands for atomic mass unit. So 1 AMU is equal to 1.67 times 10 to... Oh, look, a neutron is also 1 AMU. An electron is not 1 AMU. Electron is tiny. So like I said, Rutherford figured out that there's a very dense core and a lot of fluffy area that is not very dense. The atomic radius, the radius of an atom, is this kind of magnitude. But the radius of the nucleus is this kind of magnitude. 10 times 10 to the -10 times 10 to the -15, that's significantly different size, much smaller, this nucleus compared to the electron cloud. The electron cloud is what takes up all the space. And so because the electron cloud takes up all the space, that's the exterior of the atom. Electrons are actually where reactions take place most of the time, unless you're doing very specific nuclear chemistry like I just showed you in that last Chadwick experiment. So electrons are very, very big in the study of what we will do all semester. When reactions happen, it's happening with the electrons because that's what's taking up all the space. That's the stuff on the exterior that's available for reacting. Okay, one final little thing so that we can make sure we know the size reference. If the electron cloud is the size of Mercedes-Benz Stadium, that's what this guy is down here, the nucleus is the size of a marble sitting on the 50-yard line. Do you get that? Nucleus is tiny. Atoms are tiny on their own, but nucleus is wee little bitty, and then the electron cloud takes up all the space. Okay, I forgot that this popped up first. Neutral atoms always have the same number of protons and electrons. Why is that? Because protons are positively charged, electrons are negatively charged. They have to sum together to equal 0 if you're going to be neutral. All right. So it's time to get familiar with the periodic table. Hopefully you're already kind of familiar, but again, we're starting at the baseline here. The periodic table is composed of elements. Elements all have an atomic number. The atomic number identifies the atom. Atomic number 8 is oxygen. The atomic number also tells you the number of protons. So atomic number 1 is hydrogen. How many protons in hydrogen? 1. Atomic number 6 is carbon. So how many protons in carbon? 6. Yeah, you get it. So when we give you information about atoms, we often write the element symbol. Yeah. We give the atomic number as a subscript on the left-hand side of this atom symbol. Atomic number tells you the number of what? Protons. This is why I hate lecturing on video, because I can't make you actually answer these, but hopefully you really did answer that out loud. We put another number up top. That number up top is called the mass number. The mass number is protons plus neutrons. Remember, electrons are very light, itty-bitty, but protons and neutrons are heavy. So protons plus neutrons tells you the mass number. The mass number is not exactly the bottom of the periodic table number. It kind of is, it kind of isn't. We will talk a lot about that. But let's say this is chlorine 35. What that tells me is this specific chlorine, if I do a little subtraction and it's perfectly set up for that, this specific chlorine has 18 neutrons. The reason I know that is because that was protons, and this was the summation of them both. So this specific chlorine has 18 neutrons, 17 protons, and an atomic mass of 35. This is called an isotope of chlorine. Isotopes are things that have the same number of protons, aka it's got to be the same atom, because protons are what identifies your atom, but a different number of neutrons. So chlorine actually exists as two common isotopes, chlorine 35 and chlorine 37. The numbers that I'm saying there are mass numbers, not proton numbers, not electron numbers. The numbers that I'm giving are mass numbers. So chlorine 35 and chlorine 37 are isotopes. All right. I already said this, actually. 18 neutrons over there. So 20, you must have 20 neutrons in chlorine 37. Okay. Lithium has two major isotopes. Lithium is element number 3. So that means he's got 3 little green dots in the middle, according to my picture. No matter what type of isotope he is, he's got 3 little green dots. But if he's lithium 6, he's got 3 little red dots, 3 neutrons. If he's lithium 7, he's got 4 little red dots. I know, all my arrows are the same color. It's hard to tell the difference. I know. Isotopes are naturally occurring in our world. Isotopes have predictable percentages in the world. 92% of the lithium on our planet is lithium 7, while 7% of the lithium on our planet is lithium 6. If you look on the periodic table says the mass of lithium is 6.9. Is there any lithium that's actually 6.9 on the planet? No. There's lithium 6 and lithium 7, and the periodic table contains an average of the isotopes that exist. That's another day, actually. We're just doing subatomic particles today, and one other thing. Okay, so I said a neutral atom has the same number of protons and electrons. That's because those have opposite charges. Those must cancel out to equal 0. If you do not have the same number of protons and electrons, you are going to be an ion. An ion is an atom that has a positive or a negative charge, aka unequal protons and electrons. Sodium, that is neutral, has 11 protons, 11 electrons. Sodium that's positive is positive because it's got 1 less electron than it does a proton. So protons are positive, electrons are negative. You get a net positive when you lose an electron. This really trips up students for a while when they first learn of this. But remember, electrons are all the fluffy cloud. You do not, in general, you do not add or subtract protons or neutrons to atoms. You only add or subtract electrons. So in order to make this kind of molecule, a positively charged molecule, you're going to subtract an electron. In order to make a negatively charged molecule, you're going to add an electron. Electrons must be the thing that you manipulate. You are not manipulating protons. If you manipulate protons, it's a different atom overall. Things that have positive charges are called cations. Yep, that's easy-ish for me to remember because that T in the middle looks like a plus charge. It's really what I thought about back in the day when I was learning this. An anion is something that has gained electrons and has a negative charge. Cations are positive. I've seen another, cats have paws. That's another way that people are taught to remember it sometimes. Anions have negatives, but you're only changing the electrons either way to make cations or anions. All right, so here's our periodic table, and these are the typical ions that they make. Do you notice a trend? I hope you do. These green things all have what kind of charge? Positive. These reddish things all have negatives. These are cations. These are anions. The green ones are actually all considered metals. The red ones are considered nonmetals. This is getting a little bit deep for what we need to know right now, but metals are much more loosey-goosey with their electrons. Metals are much more likely to get rid of electrons. Nonmetals are much more likely to accept electrons. So nonmetals take on electrons, become negative. Metals give away electrons and become positive. So students sometimes say, how am I supposed to know these charges? Am I supposed to know these charges? Unfortunately, yes, you are. It's not so hard. Things in the first column like to lose 1 electron, so they become a +1. Things in the second column like to lose 2 electrons. We'll talk about why they like to lose those later, but they like to lose 2 electrons, becoming a +2. Things in the next to last column, they like to gain 1 electron, so they become a -1. The next to last, yeah, I just said that. I know it's weird. It's okay. They become -2s. These become -3s, -4. But there's this weird transition between things here. Depending on what kind of periodic table you look at, you might see a little stair step across these things. Some of the stair steps don't always go quite as far as I drew them exactly, but that stair step, things that actually touch the stair step are a little bit confusing sometimes because they could potentially be positive or could potentially be negative. They are the transition of metal to nonmetal. They're called metalloids. We will talk about those a little bit more, but some of them, like this one, aluminum is always a +3. Aluminum does not become an anion when you take or give electrons to aluminum. It always gives electrons. Okay. So a couple of things we have to know about the periodic table. We can't really study a lot of chemistry without knowing some periodic table stuff first. First, note this little stair step thing. I told you things that touch the stair step. Those are the gray ones. Those are called semimetals. That is green and not gray. I know, I'm sorry, but semimetals, sometimes called metalloids. The green ones, metals, the blue ones, nonmetals. Hydrogen over here is an outlier. Hydrogen likes to be in this first column for a lot of the things that he does, and he fits that kind of pattern, but he's also one that kind of fits over here and kind of fits this pattern, so hydrogen is an outlier. Be careful of him. Things you need to know. This short, squatty little section in the middle, those are transition metals, special kind of metals called transition metals. When you go across a row, we call those periods. When you go up and down a group, up and down a column, we call those groups. I'm so trained in chemistry, it's hard for me to call them different. Some of those groups have special names. This very first group are called alkali metals. The second group, alkaline earth metals. This group over here is called halogens. And this group over there is noble gases. Yeah? Just some highlights of periodic trends, periodic table, things you need to be familiar with. Okay, on to our next topic. Naming compounds. In order to name compounds, you need to know the element names. And again, you're supposed to be kind of working on that. There are some we will see much more commonly than others, and you'll just kind of get familiar with them through practice, I hope. But you might need to reference a list when you're first doing your homework soon. So in order to name a compound, you have to be able to classify it according to two big categories. If you have a nonmetal bonding with a nonmetal, those things are called molecules. If you have a metal bonding with a nonmetal, those things are called ionic compounds. So ionic compounds are named according to one set of rules, while molecules are named according to another set of rules. Calcium is a metal. Oxygen is a nonmetal. When those guys become bonded, they form an ionic compound. Ionic compounds. They're often solids, but not always. Molecules, though, molecules can be combined in tons of different combinations. Water is a molecule. Carbon tetrachloride, I just named it. Carbon tetrachloride is also a molecule. These are often, but not always, liquids. It's because of how they interact with each other. Let me explain a little bit further. When calcium, if you have pure solid calcium, calcium that has no charge, neutral calcium. Neutral calcium is not super stable. Calcium would much prefer to give up 2 electrons and become a calcium 2+. Oxygen, neutral oxygen, O, not diatomic O. We're going to talk about that. But neutral oxygen, just a naked little oxygen atom, not super stable on its own. It would much rather gain 2 electrons to become an anion, an O2-. So this is a match made in heaven that when you hook these two together, this calcium can give those electrons to the oxygen, makes the calcium happy because he lost them, makes the oxygen happy because he gained them. So they become, like I said, an ionic pair, a match made in heaven, calcium oxide. Anytime you have total transferring of electrons, that's an ionic compound. And total transferring of electrons happens when you have a metal with nonmetal. That was a lot. When you don't have total transferring of electrons, when you draw bonds, like these little bonds right here, we are getting way ahead in what we're learning, I know, but sometimes it's really hard to build the foundation without telling you why it matters. When we draw little bonds, those bonds represent electrons that are shared between these atoms. This one, totally transferred. These are shared. The reason these share is nonmetals are very friendly with each other. They are very good at sharing. Okay. The point of today is naming the compounds. In order to name it, you have to know if it's a molecule or an ionic because there are different rules for those different compounds. Ionic compounds, cations, anions, metals, nonmetals, always. Metal, nonmetal. Yep, click, got it. Because these ionic things have to totally share electrons, they must become a neutral molecule together, a neutral compound when they're combined. So you have to make sure your charges cancel out completely. In order to make sure their charges cancel out completely, you need to be familiar with the periodic table charges, as in lithium is always a +1, calcium is always a +2, fluorine is always a -1. You need to be familiar with periodic table charges, like we just discussed, but you also need to be familiar with polyatomic ions and their charges and their names. These are all anions except for this very first one, but you need to know that carbonate is CO3 2-. We always write it in that way. I know that disturbs some students, but this is CO3 2-. It's not CO3 -2. I know. It's a little point, but it's unfortunately a big deal. So carbonate, bicarbonate, chlorate, cyanide, those are polyatomic ions that you need to know, because that's the root, the foundation of being able to name compounds, is you got to know what their components' names are. All right. Okay. So here are a couple of examples that we're going to breeze through. Aluminum oxide. Number one, you need to know that aluminum is Al. And you need to know oxide, that actually means oxygen as an anion. So that last slide actually talks, oh no, it didn't. I thought it did. Apparently I ignored that and didn't put it there. The typical charge on an aluminum is a 3+. The typical charge on an oxygen is a 2-. If you just put those together, do they cancel out completely? No. So that means they're going to have to combine in a different ratio in order for the charge to be balanced. So the best case scenario is to multiply this one by 2 to come up with a total +6 charge from our aluminum contribution. Multiply this one by 3 to come up with a total -6 charge from our oxygen contribution. So we got +6 and -6, they're going to cancel out now. So what that really means is I need aluminum, I need 2 of them, to combine with oxygen, 3 of them, in order to make a totally neutral compound. I don't remember the name of the rule, and I should maybe pause to look it up, but I'm not going to. Yikes. One shortcut way this is done is to take the charge on the atom and pull it down to be the subscript on the atom it's combining with. Take the charge on the atom and pull it down to be the subscript of the atom it's combining with. Disregard charges when you do that, but when you do that, you end up with the proper formulation of the ionic compound aluminum oxide. There is no way that you can have aluminum oxide unless it's 2 aluminums and 3 oxides. Yeah? Calcium bromide, that's a Ca and a Br. Calcium is a typical +2. Bromide is a typical -1. The way these combine, if we do our little shortcut thingy, it's a calcium. If your subscript is 1, it is always excluded. If your subscript is 2, it must be included. So calcium bromide is CaBr2. If you say that to someone in your class, they need to understand it. If you said that someone to another chemistry class, they need to understand it. They will understand it. If you say that to someone across the country, they will understand. Calcium bromide is CaBr2. Sodium carbonate, that's Na, and carbonate is one of those polyatomics. That's CO3. Carbonate is CO3 2-. Sodium is always a +1. When these things combine together, they always form Na2CO3, period. If you ever have or ever need multiple units, multiple things of your polyatomic needs to be put in parentheses. So we would have put something like a CO3-2. This is not valid for this exact example. I'm just telling you of things to come. This is really Na2CO3, sodium carbonate. Okay, moving on. Ionic compounds, metal, nonmetal. Have I said that enough times? The anion is named an ide, or you use the polyatomic name. BaCl2. So now we're going backwards. If we're given the molecular formula thing, brain fart, we have to come up with a name. Ba, that's barium. Cl, that's chlorine. But as an ionic compound, that's chloride. So this is barium chloride. K, that's potassium. Oxygen, but it's got to be an ion, so that's potassium oxide. I don't have to put any numbers in these things because the charges of the elements tell me how many of them need to be combined. If I have magnesium hydroxide, magnesium is Mg, and that's always a 2+, and hydroxide is a polyatomic that I need to be familiar with, that's OH-. So this is an example of one that needs a parentheses because you need 2 hydroxides to combine with every magnesium. Mandatory, absolutely must have that hydroxide in parentheses. MgOH2 is not the same as Mg, parentheses, OH2. This is totally wrong. You get all your points taken away. Take them. Potassium nitrate, that's KNO3. Na2S, that's a sodium and a sulfide. Yep, that's ionic compounds. One little stumbling block with ionic compounds is when you have a transition metal. If you look back, way back when we talked about the periodic table, transition metals can have multiple charges frequently. And so you do need to include a number when you're naming an ionic compound that includes a transition metal, because they can be multiple charges. So FeCl2, because I know Cl is a -1, that must mean that the Fe combined with it is a 2+. So this is iron 2 chloride. Same but different. This is iron 3 chloride. Pulling those charges back up, this is chromium 3 sulfide. There's actual math there of how that works. Ionic compounds. If they're not transition metals, it is super simple, super straightforward. If it includes a transition metal, you got to include Roman numerals. Molecules, that's the nonmetals and the nonmetals, remember, You have to include prefixes to tell you how many of that thing are included. Molecules, because they can share in many, many, many different ways, it's not a predictable number when they're always combined. You'll see what I mean. There's our table of prefixes that we will use. The last element always ends in "ide." Some of them have common names like water and ammonia and methane. And right now I am totally blanking on the name of this one. It'll come to me as soon as I hit stop on this recording. HI, that's hydrogen iodide. You do not have to say monohydrogen monoiodide because mono is often excluded. NF3, that's nitrogen trifluoride. You have to tell me how many of each atom are included, except the mono is often excluded. Sulfur dioxide, that's an S with an O, but two of the O's. Dinitrogen tetrachloride, N2CL4. Nitrogen dioxide is this guy. Dinitrogen monoxide, that's how I was getting ahead of myself a second ago. These two are interesting because if you combine it in a 2-to-1 oxygen to nitrogen ratio, it's a toxic chemical. If you combine it 2-to-1 in a nitrogen to oxygen ratio, that's laughing gas. Molecules can combine in many, many, many different ratios. Oh, we got to wrap this thing up. An acid is something that produces H+ when it's dissolved in water. HCl as a pure substance, it is hydrogen chloride. But when you dissolve HCl in water, it produces H+ ions. And so producing H+ ions makes it an acid, and naming an acid is different from naming a molecule. So this becomes hydrochloric acid once you dissolve it in water. An oxoacid is also something that produces H+ in water, but it has an element, a hydrogen, and a whole bunch of oxygens. Nitric acid is an example of an oxoacid. An element produces H+ and a bunch of oxygens. Carbonic acid, another, an element produces H+ and has a bunch of oxygens. And sulfuric is the last one we'll talk about now. Bases are things that yield hydroxide ions when dissolved in water. Some of our favorite bases are sodium hydroxide, potassium hydroxide, and barium hydroxide. Note all of these compounds are ionic because they are metals combined with hydroxide. So you follow the ionic naming rules that we discussed way, way back. I'm done. That's enough for today.